Test. All right, let's see. So this is, I'll say, the second half of the double spending problem. So I introduced a little of the theoretical background and some of the pieces in the first video, number 9. And so in this one, I am introducing some of the details of how the double spending idea is prevented. So, say Alice would like to send money to Bob and then Bitcoin, but then also Alice would like to send money to somebody else. It could be herself, but let's just, be C. So Cindy, I think, is the usual other person. So double spending is to send money to both parties, and that would be the double spending. So the same Bitcoin. So how could you possibly do that? Well, so then what does that even mean, to spend money? So in the blockchain, and it's broken up into segments. So there's this long ledger, it gets longer, roughly every 10 minutes. And then in here are a series of transactions of inputs to outputs. The outputs then show which accounts have a certain amount of Bitcoin in them. So these outputs. So in order to spend, a spend is considered legal under a few conditions. Some important ones are the transaction request has to be signed signed by the input owners. So it does not have to be signed by the output owners, but everybody who's putting money into the pot has to sign off on the transaction. So a transaction has to be signed in that way. So let's say Alice creates 2 records using inputs that she has control over because she has the private key that allows her to create these signatures. So this requires the private key. So Alice controls the private key and therefore can sign transactions that would spend that row out of the transaction ledger. So she signs something like this, but then she signs 2 of them. So one, the output goes to Bob, right? And then there's another one where same input, but the output goes to Cindy instead. And then she maybe broadcasts, so let me erase a little bit. Brag. So she broadcasts these to the network and maybe tries to do a few things. So let me describe what happens next. She assigned these things. She then broadcasts them to the Bitcoin network, and the Bitcoin network contains nodes, and they're randomly connected by the internet. Okay, so these are all nodes that are connected to each other. And so she broadcasts those transactions, and one of the ploys, right, it's not like they all know all the transactions simultaneously, because it's the internet. It takes a certain amount of time to do transfers. There could be problems with connections and that sort of stuff. So again, this is about building a consensus. So there are a set of transactions that's called the mempool. So transactions that are signed, that are sort of okay, they pass the test of being okay, but they're not on the blockchain. So they're just transactions that are out there. So Alice maybe puts these in the mempool. If she's really trying to double spend, maybe she drops one kind of at one end of the network and the other one at the other end of the network, in the hopes that somehow the network accepts both of them in time for Bob and Cindy to think that they've been paid in this transaction. So the next role is, I guess these nodes are colored, and some of them are the miners in here. But what the miners do is they collect some subset of the transactions that they are aware of in the mempool. They might actually be different. They could be quite far away from each other in the network. But the miners collect these transactions and make a block, right? So in that block, they introduce a row that gives money to them. That's the block reward. And also in all these transactions, there's some unspent coin. And so they add themselves as the recipient of all that unspent coin. And that creates a block. Now, the miners that are on the network don't have to choose the same set of transactions. I mean, it's certainly unlikely that they would have the same sort of signature because they would rather have the money go to them than to some other miner on the network. What they do make sure is that the transactions are legitimate. So compared to their estimation of the blockchain, they see that this transaction is signed by all the inputs, and it doesn't represent a row that's already been spent, that transaction output, the inputs of those transactions contain the amount as stated, basically, that money is available. So it's a valid transaction in that sense. So it's been signed by the owners of the inputs, and the owners of those inputs actually have the inputs that they claim to have. Like if you go through the history of the blockchain, that's in the record. All right. So essentially, make a block of legit transactions. And like going on with this double spending problem, maybe by Alice like dropping into the mempool near this node, one of the transactions, and near this node, one of the other transactions, then let's assume that they don't easily communicate with each other. They have to go a long ways to get there. Then maybe this miner includes Cindy, right, as one of the legit ones. And over here, doesn't even know about Cindy. And this one includes Bob in the transaction. So then they do this proof of work puzzle. So they add the transaction. They have this block. It has all these ledger items on it. And they're trying to get to the point where they get this proof of work check off, which then allows them, this is part of the randomness, to be to have a record that shows that they worked really hard and has a set of transactions that they've taken to be legit. So, in sort of the good world, right? All the miners, and there's no double spending, so there's some history of these sort of checks, right? Going back in time, which is the current state of things. It goes quite a ways back. Let's say one of the miners wins the proof of work puzzle, right? It's a random thing. So sort of the most likely first thing to happen is that one of these two wins at substantially different time than the other one. And then the network just accepts, and the rule is accept the longest chain. So the rule would just accept either the Bob transaction or the Cindy transaction because it showed up first. And so then the new broadcast chain would just be the longer one, and it would include one of the transactions and exclude the other one, because now once this is, say Cindy's the one that was the winner here, right? That means this set of transactions could no longer be added because it would no longer be legit, because as you'll go through looking through the history of the transactions, the Cindy transaction would have erased the amount that would have allowed the Bob spending to even happen. So that's sort of maybe case one, sort of nefarious case one. Nefarious case two is the timing is really good, and both the miner here and the miner here at a time so close to each other they couldn't sort of share information across the network in any way, both win a proof of work puzzle, and now there's two chains that are the same length. So you have one here and one here, and they are the same length, and they're both legit because this one only includes the Bob, say, this one includes only the Bob chain or the Bob transaction, and then there's another one that contains the Cindy, um, and now there's two possibilities of what to create. There's two futures, right, about transactions. So the rule is to accept the longest chain, and so the mining will now continue by some nodes on these two equal chains, right? But because of the randomness of the second set, there'll be one of these two will then win at the second game. It's not exactly 10 minutes that happens, right? It's just a likelihood. On average, it's 10 minutes, but the network has this randomness that makes it quite unlikely that both of these chains, the second time through, would then also get through the network at the same time, and there would be a winner. And once one of them got to be the longest chain, then the rest of the network, by using the longest chain rule, would accept that as the correct one. So and that's what is important about waiting a few transactions before being confident that such a thing did not happen, right? It would be quite unlikely for that race to be won 6 times in a row with such a timing fidelity that the network was confused about which one was the longest one. So that is what really prevents the idea of double spending, because as these miners are randomly adding elements to the chain, they the longest chain rule just makes one of them legit, and you're not allowed to add a new element to a single chain unless all the transactions from the beginning of time forward are okay. So if they're not okay, then you wouldn't be able to, like, nobody would accept a transaction block by a miner. The rest of the nodes would not accept a block that had a proof of work, but had like an unsigned transaction or a transaction of money that was, or Bitcoin that was already spent in some other transaction. So it just wouldn't be counted. It would be ignored by all the other nodes, and so therefore it's just not a legitimate block to even think about. So there's the core of how the Bitcoin network manages to achieve this network consensus on what is the ledger at the moment. And so that is the conclusion of my second video.